Today we're going to talk about modified unit analysis and the radius. Now you may think that it is overkill to make a whole video on the radius, but I think you will see that this is an important topic and it needs to be dealt with. Now I think everyone will agree that we can't really talk about the radius unless we're talking about the circle. Okay, so the radius is the distance from the center of a circle to the outer edge of a circle. Now, if you had an ellipse, then you can maybe have two radii, one for the long axis and one for the short axis. But for now, we're just talking about the radius of a circle. And of course, the relationship between the circumference of a circle and the radius of the circle is circumference equals 2 pi times the radius. So if you have the radius of a circle, you can calculate the circumference, and if you have the circumference of a circle, you can divide by 2 pi and calculate the radius. And it is well known that the standard units of radius, the units of radius that you would find in the NIST standard, is the meter. And this is what I'm calling into question in this video. In modified unit analysis, the units of the radius are not the meter. And as you likely remember from my previous videos, the circumference of a circle is also equal to the wavelength of the circle. So circumference and wavelengths are intimately connected in this manner. And I've shown you a video of how this works, but this is actually geometrically more accurate. The circumference of this circle is approximately the wavelength of this wave, and so I actually equate the circumference of a circle with the wavelength of a wave, and they both have units meters per cycle. And so wavelength and circumference are 360 degrees. Okay, so this is really saying meters per 360 degrees, or you could say meters per 2 pi, or I could make up a unit called the Doge. Okay, in the Doge, one turn around the circle is 720 degrees, or sorry, 720 Doge, and one Doge is equal to a half a degree. And so once around the circle is 720 Doge. So that's what the units would look like. But here's the problem. I don't want to put numbers into the unit section. That's why I put a symbol here. Okay, it's meters per whatever units I'm using in my experiment. So if I'm using degrees, so here's an example. So here's the relationship between circumference and wavelength. Okay, here you have a circle with 30, 60, 90, 120 degrees being marked out. And here is a wave with 30, 60, 90, 120, whatever degrees up to 360 degrees. So this is 360 degrees, and once around the circle is 360 degrees. So long story short, in the domain of wavelength, in the domain of circumference, in the domain of cycle, aka 360 degrees, the wavelength circumference has units meters per cycle. Okay, so the units of wavelength in my language is meters per cycle, and of course you already know that. In a similar manner, the units of radius in modified unit analysis are meters per radian. So basically all I'm doing is converting from meters per cycle to meters per radian. So as I mentioned in a previous video, the radian, 1 radian is the angle such that the arc length equals to the radius. So radius and radian are intimately connected, and as 360 degrees has units meters per cycle, 57 degrees has units meters per radian. So 1 cycle is 360 degrees. 1 radian is 57.29 degrees. Okay, and so the circumference of a circle, 1 wavelength, has units meters per cycle, and 1 radian, so 1 partial cycle, because this is not a complete cycle, 1 incomplete cycle of 1 radian has units meters per radian. So meters per cycle are the units of the circumference of a circle, and meters per radian are the units of a partial circumference of the circle, which just happens to equal the radius. So whenever I see radius, I'm going to assume we mean these, because you're not going to have a radius unless you have a circle or maybe an ellipse. But you're not going to have a radius unless we're talking about a circle. And I think because the radius equals this arc length here, that we are in fact, at least in the own particle model and in modified unit analysis, I'm actually referring to this arc length here. So whenever I see radius, yeah, I'm going to think about the radius of the circle, but I'm also going to think about the arc length of the circle. And then the question I want to ask you is radius fundamental? Is radius fundamental? That is the question I am asking in this video. Is radius fundamental? Does nature care about radius? Is the radius of a circle a fundamental measure of nature? Should, when we take all of the constants of nature and combine them together and get something that get the units of the meter, are we going to assume it is a radius? Or are we going to assume it is the circumference of a circle, or maybe it's the diameter of a circle? But is the radius important? Because radius does seem to be very important in physics, okay? I'm not saying it's not useful. I'm just saying the question is, does nature care about the radius? If it were going to spit out fundamental constants, would those constants be in terms of radius? And so here is just a quick picture of what I mean. When you want to measure the radius of a tree, you cannot measure the radius of a tree, of course, unless you chop down the tree. So the way you measure a tree is you put a string around it, you put a measuring tape around it, and you measure its circumference. And then if you need the radius for whatever reason, you can calculate the radius. Or if you need the diameter, you can calculate the diameter. But really, you cannot physically measure the radius of a tree out in nature without cutting down the tree. So again, is radius fundamental? Does nature care about radius? Do we see radius in our equations that we use to describe nature? Well, it looks like we do. It looks like we do. What we find is in the gravitational equation and the electric charge equation, where you're calculating a force, in this equation you see something that looks like radius in the equation. But is this really a radius? So when you look at charges, okay, let's look at the charge one first. When you look at charges, now this equation only really cares about the distance between the charges. There's no orbit going on here where you have the radius of an orbit. There's no radius in this picture right here. All you have is distance between the charges. And so really this equation should read like this, where this is a d for distance and not r for radius, because there is no radius in this picture. A similar thing can be said in terms of the gravitational constant. Okay, gravity doesn't care about radius. Okay, yes, if this object is orbiting around this object, then this is going to be the radius of the orbit. But this equation here really only cares about the distance between these objects. And really, this is just at any snapshot in time, all we have are the distance between these two objects, and so regardless of whether one is smaller than the other. And so basically what used to be thought of as a radius should in fact be a distance between particles, distance between planets, distance between planetary objects. And so you can see clearly here that radius, at least in these two equations, radius is not fundamental. Distance between objects is fundamental. We need to know distance between objects. But in both these cases, this has nothing to do with radius. In the own particle model, I only care about the circumference of the circle, which is the Compton wavelength, and the distance between these two objects here, which is a distance and not a radius. Although in the own particle model, the distance between these two points here actually does equal the radius of this circle. So that is actually just a coincidence of the model, but I would never put radius into my equations because I'm not talking about radius. I'm talking about the circumference of the circle, and I'm talking about the distance between these 2 points. So in physics, you often run into these 2 characters. Okay, this is the Greek character lambda, and this is lambda with a stick through it. I'm not sure if that has a name. But so this symbol is the symbol they use when they're talking about wavelength. And this symbol here is what they use when they're talking about reduced wavelength. Well, what is reduced wavelength? Reduced wavelength is actually wavelength divided by 2 pi. Okay, so when you divide wavelength by 2 pi, what's happening is you're switching from the domain of the cycle to the domain of the radian. So if you're talking about a circle, when you switch from lambda from the wavelength to divided by 2 pi to the reduced wavelength, you are switching from the domain of the cycle to the domain of the radian, or the domain of the circle to the domain of the radius. So when you're talking about a circle, you're switching from the domain of the circle to the domain of the radius. And when you're talking about waves, you're switching from the domain of the cycle, the domain of the wavelength, to the domain of the radian, okay, the arc length of 1 radian. And so you're switching from a perfectly complete cycle to a not perfectly complete cycle. Okay, you're switching from the domain of the cycle to the domain of the radians. And this is what I'm trying to avoid. Okay, I'm trying to avoid this. I'm trying to do all of physics in the domain of the cycle. And that cycle is either once around a circle, or that cycle is once along this length. Now, when you look at this diagram, you can see clearly that, okay, once around the circle is 1 complete wavelength. Okay, halfway around the circle is half a wavelength. Okay, radian is somewhere in here. So you have 0, 30, 60, 90. Okay, 1 radian is 57.29 degrees. So it's in here somewhere. So when you look over at the map, so you can see 0 is here, 30 in the circle is over here on the wave, 60 on the circle is over here. So 60 degrees in terms of a wave is right here. And so 57.29 degrees is somewhere in here. So it is it's a very arbitrary location on the curve. Okay, 1 radian, 57.29 degrees, lands around here on the curve. And this is a completely arbitrary location on this curve. So when people switch from the domain of wavelength, from the domain of complete wavelength to the domain of reduced wavelength, they are basically counting or they are switching to an arbitrary position on phase in the wave and making that fundamental. Okay, they're making that fundamental. This is not fundamental. This is the point I'm trying to make. Radius is not fundamental. Nature doesn't care about radius. And radian right here on the curve is not 1 radian, is nothing special. It's just an arbitrary position on this curve. And for some reason, the standard physics wants to do everything in the domain of the radian. They want to do angular frequency, and they want to switch everything to the domain of the radian. And that is what I'm trying to avoid. I'm actually getting a lot better interpretations when I switch to the domain of a cycle, because nature is not quantized by the radian. Nature is quantized by the cycle. So where else is radius being used? Where else in the language of theoretical physics is radius a thing? Okay, so there's this one right here. This is actually the equation for the classical electron radius. What you see here is a bunch of supposedly universal constants that we know, measured constants like the speed of light, permittivity of free space, the mass of the electron, and the charge of the electron. Okay, these are all plugged into a formula. And because when you combine all these units and simplify, you get the units of the meter, they refer to this as the classical electron radius. But why did they assume that this was a radius, right? Why did they assume it was a radius and not the circumference of a circle or the length of a wave? So why did they assume this was a radius? Just because these values spit out the units of the meter doesn't mean that this is a radius. So if it's not a radius, then what is it? Well, in the own particle model, there are two choices. It could either be the circumference of this circle, or it could be the distance between these 2 points here. Okay, so, but actually I don't see classical electron radius in my own particle model. Okay, I can't find it. It's just not there. So it's not the distance between, if the circumference of this circle is the Compton wavelength, which it is in my model, then this cannot be the classical electron radius because it does not work out to be the correct value. So what if instead of assuming that this is a radius, why not assume that it is a wavelength? Okay, so what happens when you assume it's a wavelength? Well, in terms of the own particle model, that actually doesn't help me much, because this is also not the value of the circumference of my circle, which is supposed to be Compton wavelength, and the distance between these 2 points. Okay, and so what I want to know what's the relationship between this modeled as a wavelength. What is the relationship between this and the Compton wavelength? Because in my model, the circumference of the circle and or the wavelength of my own particle model is the Compton wavelength. And so what happens when you divide these two? What happens if you take the classical electron wavelength? Now we're just modeling this as a wavelength. We're pretending it's a wavelength, okay? So this wavelength divided by the Compton wavelength, which my model assumes as the circumference of the circle or the wavelength of the wave. When you divide these two together, you get this number here. Now, anyone out there that's a little savvy will recognize this as the anomalous magnetic moment. Okay, so this is the anomalous magnetic moment. If you pretend that the classical electron radius is a wavelength and you divide it by something that I am modeling as a wavelength, so you're comparing apples to apples here, you're comparing something I believe is a wavelength with something that I believe is a wavelength, you get the anomalous magnetic moment. So what happens when we do model this as a radius and compare it to the Compton wavelength of the electron? And so when we model this as a radius and compare it to the Compton wavelength of the electron, we need to divide by 2 pi. So we need to convert this to radians, aka radius. So when you do this right here, when you convert this to the domain of the radian, of the radius, and compare it to this radius, you get this value here. And of course, you'll recognize this value here as the fine structure constant. So I find this really interesting. Okay, so although the classical electron radius, this value here, has no meaning in my own particle model, okay, since this has no meaning, this is not meaningful, but when I apply this conversion factor, when I apply this conversion factor to the to this value here, the classical electron radius, you end up with the in the domain, you end up with actually calculating the distance between these 2 points, which also happens to be the radius of this circle. Now, in the case of when you model the classical electron radius as a wavelength, when you model it as a wavelength, we get the anomalous magnetic moment. And so to me, it seems like both the anomalous magnetic moment and the fine structure constant basically are 2 sides of the same coin. When you're in the domain of the radius, when you are in the domain of the radian, so when you take the circumference and divide it by 2 pi, you are in the domain of the radian. When you're in the domain of the radian, aka the domain of the radius, you need to use the fine structure constant. And when you're in the domain of the wavelength, when you model this as a wavelength, you use the anomalous magnetic moment. So these two appear to me to be 2 ways of expressing the same thing. Okay, here is the fine structure constant in the domain of the radius, in the domain of the radian, and here is the anomalous magnetic moment in the domain of the wavelength. Okay, so these appear to be 2 sides of the same coin. They appear to me as some sort of conversion factor. And I think I know what the problem is. So I'm just going to give you a brief slide explaining what I think the problem is, and then give you time to think about it before I elaborate more. So what I'm going to do is I'm going to switch to the domain of the wavelength. I'm going to assume that this is a wavelength, and then I'm going to have a look at this a little closer to see whether maybe there is a problem in here. And so these are all fundamental constants. This is the permittivity of free space. In fact, this right here is the Coulomb constant. Now, I don't know why they have to write it like this. I would rather see a little letter K here for the Coulomb constant, but this is in fact the Coulomb constant, and the mass of the electron is known, and the speed of light is measured and known, and supposedly this is measured and known, but we are going to have a closer look at this. So there is another quantity of charge that is found in the literature, and this is referred to as Planck charge. And this can be calculated in 2 ways. So there are 2 calculations for this. One of them uses Planck's constant straight up, and one of them uses h bar, which is Planck's constant divided by 2 pi. Now this is the one we're going to be using because I am in the domain of wavelength. So I am in the domain of wavelength in all of the cosmology that I'm doing. I am switching from radians to the domain of radians to the domain of cycle. And so I am always going to use h, Planck's constant, and I'm never going to use h bar. And so I'm avoiding the radians. As soon as I use h bar, I have to use omega, I have to use angular frequency, and I don't want to use angular frequency, I want to use cyclic frequency. So every calculation that I do, you can assume that I'm using h and not h bar. So what I'm going to do for fun here is I'm going to replace elementary charge here, elementary charge squared, with Planck charge squared. Okay, so I'm going to perform the same calculation, only I'm going to replace elementary charge squared with Planck charge squared. And when you do that, what you end up with is the Compton wavelength of the electron. When you plug these values into this formula, you end up with the Compton wavelength of the electron. So this is really nice for my own particle model, because the own particle model has the circumference of the model, the circumference of the circle is the Compton wavelength of the electron. Okay, so, or if this was the proton, if you plugged in the mass of the proton here, you would get the Compton wavelength of the proton. So this, to me, looks really fundamental. What happened to alpha? So where did the fine structure constant and the anomalous magnetic moment come from? Well, it turns out when you take elementary charge squared and divide it by Planck charge squared, now keep in mind this one was calculated using h, Planck's constant, and not reduced Planck's constant. When you do this operation here, you get the anomalous magnetic moment. But when you take elementary charge squared and divide it by Planck charge squared that I calculated using h bar, so reduced Planck charge, basically, you get the fine structure constant. Okay, so you get the anomalous magnetic moment if you use Planck charge where I used h, and you get the fine structure constant when you use Planck charge calculated using h bar. Okay, so clearly you can see that the anomalous magnetic moment and the fine structure constant are related, and they have something to do with the relationship between the charge as we calibrated it in our system with Planck charge. But regardless, when I substitute Planck charge for elementary charge in this formula that's meant for calculating the classical electron radius, I get something that is familiar to me. I get the wavelength or the circumference of my own particle model of the electron. Okay, and again, if this were if I replace the mass of the electron with the mass of the proton, then this value would end up being the Compton wavelength of the proton. And as everyone knows probably by now, both the anomalous magnetic moment and the fine structure constant, which are the same thing, which are not two different things. They are the same thing. When you're in the domain of wavelength, you use the anomalous magnetic moment, and when you're in the domain of radians, you use the fine structure and constant. Regardless, this constant, whether it be in wavelength or in radians, is a unitless value. And whenever, as a computer scientist in the 3D ultrasound acquisition software that I develop, when I find a unitless value, but I don't know why, it almost always turns out to be a calibration error. And so to me, it seems like maybe we calibrated charge wrong, or maybe charge is calibrated for the domain of electronics, but maybe it shouldn't be used here. I'm not sure. Okay, I'm not sure, but it looks like when I use Planck charge, I get values that I am familiar with. I get values that match what I expect to find in my model. And so that gives a little bit of, to me, it gives a little vindication to my model in the fact that I'm able to calculate one of the parameters from my model using the constants of nature. And so that is the point I want to make. The main point I want to make is that the units of the radius are meters per radian in modified unit analysis. Okay, so I'm going to be very strict about that, okay? But I'm going to try to avoid the domain of the radians, and I'm going to always stick to the domain of the cycle and the domain of the circumference of a circle, and not the radian. Okay, so I'm going to try to avoid radians. Whenever I see angular frequency, I'm going to convert to frequency. Whenever I see wavelength, I'm going to convert to frequency. So I'm going to stick to the frequency domain, and I'm going to stick to the domain of the cycle, one complete cycle, not one partial cycle. And so that was the main point. I took a little journey here on this video, but that was the main point I wanted to make in this video. And so hopefully you kind of get the point that the circumference of the circle and the wavelength of a wave are really two ways of looking at the same thing. And so the circumference of my own particle model is also the wavelength of the particle as a, if you can think of this as a standing wave. This is a wave that is propagating in place, and light are waves that propagate in through space. Okay, so this is the own particle model. This is an electron. This is a proton. Probably other particles too, but for now, I want to focus on the electron and the proton. Okay, so that's about it. I hope you're having a good day, and I'll be back.